efficiency. My queries are running slow. What do I do? Yeah. Okay, so here's my list of aspects of efficiency, database efficiency. So obviously what hardware, software you choose, talked about that, makes a difference to how fast things are going to run. How your schema is designed is potentially going to affect the speed of how your system runs, or will. Correct data types, the more bytes, wasted bytes, the slower the system. Remember, use the minimum data type that encompasses the range of the data that you're using, etc. Otherwise, you might end up with a database 2-3 times the size that it actually needs to be, and consequently significantly slower. There is the issue of normalization and denormalization of your database schema. So far we're concentrating on normalized data structures. Next week we're going to visit denormalized data schemas. One of the main purposes of denormalization being simplicity, the other one being speed. So denormalized databases can be much faster than normalized databases. Database tuning, so we've got our design, we can tune the system, we've got the routine maintenance of every day looking after the stuff, looking after the system, making sure we clean out the old records, the unused records. But we can also set indexes onto fields to increase particular response of particular queries, and we'll talk about that. Not only can you create indexes, you can then undertake further optimization onto queries. You can have different system architectures, and in particular, I'm going to introduce really briefly the distributed database design as a way of increasing the sort of throughput, the flowput. And then, of course, there's efficiency of the actual interface itself. Does it take, for example, this is what people actually do. They count how many clicks involved in undertaking an action, how far you have to move the mouse physically across the screen to undertake the action. Now, I think you've done a comparison for Mike between ArcGIS and QGIS, and if you haven't done it already, you will be doing it in due course between the interfaces, which is the most efficient interface. And that can make a real difference when it comes to your end GUI users. Okay, so we are concentrating on this 3 and 4 basically here. We've done most of this. We looked briefly at benchmarking, really briefly at that, and interface design we'll talk about next year. So we're doing 3 and 4 basically. So indexes, I think we met a long time ago, and we haven't been implementing them in your databases at all, except for the GIST spatial index, which is almost done by default on all spatial fields. Why have we not done indexes? Well, simply the database isn't big enough to bother. Again, this indexes become important as systems become larger and larger and larger. Difficult to get large systems for students to play about on, really. It's not easy to do. Okay, so we'll go through the really basic principles of a couple of indexing systems. So we've got an index here. We want to find the number 25, or what do we do? Well, the most simplest thing is to do a linear search through the rows in our table. We start here, go through each value, and try and find the value that we're looking for. The larger your database is, the slower the linear search becomes. It's not an efficient way to search large databases. And adding indexes are simply ways of speeding up the extraction of data from the system. So I think I mentioned this before, indexes, a lot of indexes, in fact, just about all the indexes that every index type that I've ever come across is either a tree or a network data structure. So this is an example of the relational data model using tree and hierarchical and network data structures as part of the relational, not actually for the as part of the system that sits on top of the relational model. So here's an example of an index on a text field. So basically, here's all our people. They're in fact names. So Carl, Kathy, Kim, Nicole, Pablo, Paula, Peter, P's, R's, Raoul. So we have a whole list of names, in this case with row IDs, in a linear, effectively linear on disk. How do we get to a particular name really quickly? Obviously, sequential searches, we'd have to start at the beginning of our list, which may be millions and millions long, work our way through until we find the right person. Because don't remember, these are not all here, they're sorted into a nice order. But when you enter rows in a database, they will not be sorted by name order. For example, they'll be randomly, potentially randomly throughout the rows. So what we do is basically we have a hierarchy that points to groups of records. So at the top level, we store the indexes of, or for each record, basically we subdivide all the records into different sized groupings based in this case on the beginning letters. And then we index the records through these values. So the DI group here, so here's our, what we would have a root node of our tree would be up here, but this is the first level of our tree. So all records which start with DI or earlier in the sequence are identified with this block. All ones between DI and LU. It's a weird system, but basically you have before, you have between the groups, and then you have after there. I don't think it's the best diagram for this. But as you can see, all the DI records, then we have another level at which they're further subdivided. So all records up to B, B to C, C to CR, etc., etc. And then we carry on potentially with several other levels until we finally get one level which points to the individual groups of records that match. So if I want to find Nicole, I start up here. Nicole starts NI. I know NI is between LU and RH, so I follow there. I then go to the N record. In this case, I go there, and then I sequentially search through those indexed records. So this has taken me 1, 2, and then however many sequential scans through the N group of records to get the result, rather than potentially have scanned 10 million records to get there. So it increases return of the rows by orders of magnitude sometimes. So an index can really make one hell of a difference to how quick your responses are. So that's a simple example of an aspatial index. There are lots of other indexes for numeric values, but a B tree is your basic index for aspatial data. When it comes to spatial data and spatial indexes, as I've said just a few minutes ago, it is the norm in Postgres to build a spatial GIST index onto all spatial columns. Now, I'm not going to go into how a GIST index works, partly because I don't know the details, but it's basically, it uses a variety of different indexes and chooses the most appropriate combination of indexes to index the spatial data as best it can. So it's a kind of composite heterogeneous index, as the way I understand it as a GIST index. But one of the indexes that it does use, it would be the R tree index. This is an example. It's very similar to the B tree, but works spatially. So we've got various polygons, polygons geographically here, and basically it's a you group, it works on bounding boxes, and basically it creates a set of hierarchically, a set of hierarchical bounding boxes around groups of geometries, and then uses those as the indexing system. So here, so if I want to, for example, if my search query covers this area here, something like that, or maybe let's say, be a bit more precise, let's do this area in here. So it crosses O and P, then we know that the index, these O and P, exist at, in this case, the top level of our index up here. So instead of searching the individual geometries, we search on the hierarchical bounding box extents. So we start off, and then from the hierarchical box extents, then you can burrow down to the lower level boxes, and it either include or exclude the features associated with these lower levels on the basis of the overlap. Can't say I'm an expert on these, but the objectives when it comes to the building of these boxes, how do you build this hierarchical set of boxes? Well, they're built to minimize how big they are, to minimize the overlap between the boxes. You can't totally eliminate it, overlap, but here they minimize the overlap between the various boxes. Minimize the margins, I'm not quite sure what that refers to, and maximize inner node utilization. Not 100% certain what that means, but it's to do with how many nodes are used at each level. Basically, there's optimization algorithm to try and optimally build this hierarchical network hierarchical index. I have never needed to know about the details, the internal workings of indexes, but it's useful to have a little peek under the hood and see how they operate. And indeed, but you know, who knows, one of you, two of you might end up writing your own arch index algorithms or something like that. That's not beyond possibility. Anyway, it's just one of these peak things. You don't need to, it's just nice to know how it works without knowing the details. Now there's the question of what to index. When do you index and when not to index? The primary key is the most usual field to have an index on, and in many software systems that's automatically part of the primary key definition. Columns often used in where clauses, what a surprise. Foreign keys, if often used in joins. Columns used commonly in order or group by functions. You can build indexes on aggregate functions of values. So you could build an index of average cost. So if you regularly ran some kind of reporting system, a financial reporting system involving various functions that involve various functions, you could write index, you could set up your indexes specifically to deal with the functions and the processes that go together to create that final report to speed it up. So indexes can be generally on specific fields, but can be very much targeted towards the queries, the types of queries that are being run regularly on the system. Spatial columns always virtually have indexes, and as I say here, it's not worth it on small tables. So don't index, it's not worth indexing small tables. What's small? Yeah, how long's a piece of string? Basically, if it hurts, then try indexing it, see whether anything's quicker, whether it hurts a bit less. If it doesn't, take it off again. Indexes are not a panacea. For example, they can actually slow down your database. They are not always a good idea. So here's a little sort of meta-analogy. Consider a big index in a book. The bigger the index, the larger the size of your book, and the slower discovery in the index becomes. So there's a trade-off between the size of your index and how detailed it is, how many levels in the hierarchy of the index, and how quickly the index operates. And the other thing about indexes is that they have to be rebuilt every time the data changes. So they can be in a static system where your database is not being updated. Your indexes will, you can build your index, which may take a little while to build, and then that will work for, or be efficient for the next month, 2 months till you. But in a system where you've got constant updates of data, some kind of transaction sales-based system, then you haven't got time basically to rebuild your indexes every time some data gets uploaded. It's just not efficient. So indexes may or may not be worthwhile on transaction-based systems because of how the regularity of data update. It's all balancing. There's no way I can say never do this, never do that. It's all suck it and see, try it out, see how it works, see if it meets your needs. Query tuning. So there's setting the indexes on the fields, which will increase on sets of fields, which will increase the response of queries. There is also database administrators, high-end database users beyond my skill level can also manually optimize queries, can use the explain and analyze commands, which I think we've mentioned before, which gives you information from the database about how the query is planned and executed. Now, things like the order of the actions, what search routines are used, whether indexes are used or not, and the times taken for each of the actions. So a skilled database administrator can actually devise query plans that are more efficient than the query optimizing software can. So humans are better than computers in this case. So a skilled database designer or database person may be able to improve over the computer when it comes to the response of queries. Also, there's a design decision to be made here because you can optimize a system for one type of query which may actually slow down another type of query. And if you want to run both types of queries, then it's a balance between how important this type of query is versus this type of query. So there's a human aspect to it as well. If you want to learn more about explaining and optimizing queries, then that's a good place to start. Routine maintenance, another way. You leave your system, you don't look after anything in life, it slowly falls to bits, gets gunged up with muck. My bicycle comes to mind at the moment. Needs a good clean. Right, so garbage collecting. Remember vacuum, when you delete records in a database, they're not deleted off disk, they're merely sort of marked as being old. So vacuum regularly if you've got a database system with lots of updates, so you need to vacuum regularly. Remember the database statistics, which are used by the query planner to plan how queries are undertaken, make sure they're up to date. If your PG statistics aren't up to date, your optimizer will not be planning the queries in an optimal manner. Analyze updates PG statistics. Also monitor usage. So as a database administrator, you should understand if you've got a problem. I mean, as a general principle, you should monitor usage, but when you start to get a problem, you need to understand how the database is being used, who's using it, when, under what kind of conditions to do what kind of queries. So it may be that a problem is only periodic when somebody's running a particular job or something like that. Maybe the person needs to stop running their big report job at 10 o'clock in the morning when they go and get their coffee and need to start running it at night so that it interferes with the daily usage. The other thing is, if you don't understand the database is how the database is actually being used, which could be over thousands of people, over many countries. So we're talking, potentially global multinational companies, thousands of users, many different locations, many different users. So it may not be it may be quite a big job for the one person to actually understand who's using the system to do what. Anyway, so if you don't understand it, you may think you know what the users are doing, but you're wrong. So you're optimizing your database for some ideal user requirements type thing that was written 10 years ago, whereas the reality of it is that your users use it in a different way, perhaps, than they did 10 years ago. So you optimize to meet the real requirements, not what you think the requirements actually are of the system. Okay, just to finish off quickly, we'll look at architectures. Obviously, we do a lot more on architectures next year, but this is, so just to remind ourselves what an architecture is. An architecture is just how the components, various components fit together to make a working system. So here we've got a very simple client-server architecture, what we've been using. We've got Postgres, in our case, running on a local host, but it could have been running on a remote host quite easily. And we've been linking into two client applications, pgadmin3 and QGIS. So that's a simple client-server architecture. Now, so distributed databases. So a distributed database is a database in which the data is stored at multiple locations, not just one server running away like we've been doing, accessing it. And there are two basic types of distributed databases. There is what's called partitioned and replicated. So basically, in a partitioned database, different data is stored in different places. But whereas in a replicated data, all or some of the data is stored in multiple locations. Okay? So one is just different data, different places, bring it together. The other one is multiple versions of the same data across different machines, different locations. Whichever system it is, whether it's a partitioned or a replicate, and of course a system may be both partitioned and replicated, is that each location is effectively an autonomous relational database system or database system. It doesn't, not necessarily talking about relational systems here, any database system. Indeed, one of the things that many of the modern NoSQL databases excel in is in distribution, replication of data and things like that. It's one of the niche areas that they've occupied. So a distributed database management system is just a database management system plus some sort of distribution control system that helps them all to talk to each other and remain in sync, or at least remain functioning together. And from the end user perspective, the importance is that you don't know what the underlying architecture of the system is. You just want to access to the data. It should make no difference to the user. It should be transparent to the user whether the data is in Mumbai or Croydon or wherever it is. That should be irrelevant to the user. So a partitioned database is an example of a partitioned database. This is the National Land and Property Gazetteer for the UK. Basically, it's a database of UK addresses, basically count who issues addresses. Well, the post office maintains the postal address file, which is a list of addresses to which it delivers mail, but who creates an address in the first place? Well, that's local authorities create those addresses. And then because addresses may not be a postal delivery address, so they're slightly different things. And this system is used by when I looked, 348 local authority address creating authorities, the LAPGs, wherever they are. So there's your local authorities. We've got 300 odd local authorities in the UK. And then it integrates into a single system called the National Land and Property Gazetteer. So there's information on land and property from the National Land Information System, building location data from the Ordnance Survey, socio-economic data from the census, and the postal address files from the Royal Mail. All these, and plus the local authority data sets, get brought together under this sort of umbrella database called the National Land and Property Gazetteer. So the data on buildings is held by the OS, this is held by here, this is held by the local authorities, but there's a central clearinghouse which integrates these various data sets together into a single system. So distributed database systems can be classified in two types depending on the database management software being used. You can have homogeneous systems, in which case all systems use the same DBMS product. These are easy to design and manage and allow incremental growth. So if you're starting off from de novo distributed system, a homogeneous system might be a good idea because it's the less things you have to worry about, the simpler it is. But most sites, most examples of distributed databases, or many, run different types of database systems. So you've got maybe Oracle, Postgres, maybe an object-based model system, even a hierarchical database. And in this case, it's more complicated and you need translations to allow for different hardware, operating systems, DBMS products. So you've got to plug the whole thing together. And a typical solution to heterogeneous distributed databases is to use some kind of gateway software. So for example, who's heard of ArcSDE, Spatial Database Engine? Yeah, one, but not generally. Look it up, Arc Spatial Database Engine. We don't run it here, but it's basically it's like a sort of universal socket for databases in general. So we could plug in, so it allows us to plug in shape files and kick out GeoJSON, chuck in a geodatabase output, map info format, that kind of stuff. So it's like OGR to OGR to a certain extent. It's a piece of software which allows different things that talk different languages to talk to each other, basically. A gateway software. 12 objectives of distribution. Okay, so this is just really a list. So when you talk about a distributed database, what are the principles of a distributed database? Well, geographic autonomy. So the general idea is that, okay, we've got OS data, we've got bringing together local authority data, land registry data into one place, but that data remains, that's being integrated together, remains owned and managed by the individual organisations. There's no copy of it here. So geographical autonomy of the data. No central site is an important thing. All sites are equally remote. No one site has governing authority over any other site. So it's not a centralised system. It's meant to be a decentralised system. Continuous operation. Sites are capable of operating independently. In addition, a new site will not affect the overall system. So you've meant to be able to take away nodes, add nodes to your network without it affecting. Clearly, in the example of the partitioned model, that you can't just take away the OS and the system carries on running automatically. But what they mean is the rest of the system will continue operating. If we lose the OS because the OS has gone down for some reason, they've dug through the cable between us and them, then hopefully the rest of the system will carry on running, but you just won't be able to access the OS-related content. When it comes to duplication of data, that's clearly more relevant, or it's more directly relevant. Location independence, the person, again, just repeating the person, the users don't need to know where the data is actually stored, they just need to know how to get hold of it. Okay, yeah, okay. Basically a whole list of things. I don't think we'll bother going through all these, but these are the things that it says, is it a distributed, if we're building a distributed database system, what are the usual things to do? What are the things a distributed system should deliver or offer? Okay, so fragmentation we'll talk about in a minute. Basically, again, the user doesn't need to know how to fragment the data if it's being stored fragmented across different locations. That's up to the computer. You can make multiple copies easy enough. That when you write a query, you don't need to know where the data is elsewhere to store the queries. Transaction management is managed across distributed sites. So if you update data, it goes to one site, then how is that update propagated across the other sites? You as the user don't need to worry about that. You don't need to worry about the hardware that the various systems are running, or the operating system that hardware is running, or the network protocols that connect the different computers that run the different database nodes, etc., etc. Let's not go into those in any further detail. Okay, so at each site in a distributed database system, you have a database system, actual database management system, a transaction manager that decides whether data edits should be committed or rolled back, as in rejected, depending on the status of transactions across the whole distributed database, because you may have a conflict. You may have if you've got two versions of the same database and two updates are made to the same records on different databases, on different versions of the database, you have to then reconcile those differences. And you also need a scheduler that manages the order and timing of transactions across your network. Okay, how do they actually work? Okay, really quickly. So principles, how do you actually distribute a database? What do you do? Well, you fragment the data. You divide the relations into sub-relations, which are then distributed across the system. You can do that. So there's the process of dividing your relations, your tables, into fragments. Then there's deciding where those fragments are going to be stored across your network of databases. And then there's the question of how much, if you duplicate, and if you do duplicate data across the sites, how much data is duplicated and how you deal with reconciling conflicts between changed duplicated data. Okay, fragmentation. Fragmentation is the process of taking one relation or group of relation tables, break it into smaller tables, which are then spread across multiple database sites. Proficiency, it's most sensible to store the data close to where it's being used. The further you have to move things even over the internet, the slower it becomes. So store things close to where they're most frequently used. The lower the network traffic, the lower the network load, improve response times. It also allows us, once we've fragmented the data, distributed across multiple things, we've got the potential for parallelism, that's a hard word, parallelism of functions of software. So we can then start, so our data is distributed across multiple database nodes. We can then spread our query across those database nodes. Each of the processes on those database nodes attacks part of the problem, brings back the result. We combine the result into a single thing. So you actually have increased performance due to the parallelism of analysis. All right, okay. And the other thing is that you're not, so it provides potentially a better security model because you've not got data stored locally that is not required by people. This isn't it. I'm a beginner when it comes to distributed databases, honestly. Okay, fragmentation, really quickly. These are tables. You can fragment both horizontally and vertically. Horizontally takes a subset of the rows, stores them on different database nodes. Vertical fragmentation takes different columns out of the same table and stores them on different database nodes. And you can do mixed fragmentation, where you take a number of columns, a number of rows out of your table and store them on the different distributed data sets. So you can take either one of those approaches. Obviously, we've got to make sure that every data item must appear in at least one fragment. otherwise we interrupt. Oh, I think that's a queue outside. Okay, I think we better end there because I think that's a queue outside. But we've got completeness, reconstruction. Your system must be able to bring those fragments together to recreate the results of the query. And of course, as we know, for horizontal reconstruction, bringing together rows, we can use the union SQL command. For vertical reconstruction between columns, we join effectively. And we've got the issues of making sure that when we delete items that they propagate through the system. All right, we'll maybe just finish off for about 5 minutes in the practical, if we want.